Okay, so we were talking about last time about fossil fuels, and we talked about coal, and we started talking about oil. But there's some more stuff about oil I want to show you, and then I want to tell you a little bit about natural gas, and then we'll sort of cross the boundary in this lecture into chapter 10, I think it is, when we start talking about the climate impact of methane, because natural gas is methane, so it's kind of a natural segue there. So oil. A big question that always comes up about oil, if you read about it in the newspapers or whatever, is how long is it going to last? And there's one way to sort of calculate how long it will last that sort of takes advantage of our newfound prowess at thinking about units, at putting together a formula to calculate what we want just by letting the units sort of guide us. And it looks like this. The lifetime of the oil era is equal to reserves, so how much oil there is in the ground, and the units of that would be gigatons, we could call it, or kilograms or barrels or however, whatever sort of unit you want. And so the lifetime is, we want something in years. So reserves, and then to convert gigatons per year, we'll use the production rate, how fast we're consuming it. And the production rate is in, say, gigatons per year. So in order to cancel out this gigatons on the top, we need gigatons on the bottom. So we will assemble our formula this way, 1 over production. So now the units of this will be years on top and gigatons on the bottom. Instead of gigatons per year, 1 over it is years per gigaton. And so gigatons cancel out, and we got years on both sides. This is what they call a, in the sort of petroleum industry, the R2P ratio. There's a figure in the textbook which I would have liked to have shown you today, except I just stymied by this. Where could this cable have possibly gone? It doesn't make sense that it should just vanish, but I can't find it. There's a plot of this R2P ratio as calculated by British Petroleum. BP publishes these reports online every year. These energy fact books that have lots of tables of numbers, like how much oil there is in the ground and stuff. And they've been calculating this R2P ratio over time. So sort of from 50 years ago, what they find is that the R2P ratio has been sort of steady throughout the years at about 40 years. So it's saying that in 1960 or 1980 or something like that, there was 40 years left. And it's saying there's 40 years left today. So that must mean that they're finding more, to kind of keep up with how much they're taking out of the ground. So that makes it sound like, 40 years, that's a long time. Kind of, right? I mean, on a sort of political time scale, that's a long time. It's not something that's going to affect us right away. But there's another way to look at this, which is called peak oil. Which is also called Hubbert's peak, after Geological Survey petroleum geologist named Hubbert, who originally came up with this idea. He found that if you look at the production rate as a function of time for some oil field. So he first did this for some field in Texas, and then applied it to the continental U.S. as a whole, and it worked both times. That the production rate, how much oil you get out of the ground per time, goes as kind of a bell curve. So there's an initial part where it kind of looks like exponential growth. But it doesn't keep growing exponentially. So the exponential growth part maybe is about building the infrastructure, learning how to do it, learning where the oil is. It sort of tends to take off like that. But then it sort of levels out and plateaus at the top of a bell curve, and then follows the curve back down again. So where this really got famous was there were data from the continental U.S. that sort of looked like it was still kind of in the exponential growth phase, and it looked like the sky's the limit. We're golden forever at the time. But he estimated how much oil is going to be in the Earth in the continental U.S. overall, and then he fit a curve, this bell curve, so that it fit the data that already had happened, the past, and the total area under the curve is the total amount of oil. So this is like barrels per year is the production rate sort of unit, or could be gigatons per year or whatever. And then so this many barrels per year times this many years gives you just barrels. And so the total inventory sort of constrains the total size of the curve. If the total inventory was twice as big, you might have a curve that sort of looks like that. Or if it was half as big, you might have to fit a smaller curve to the data. But so at about this part of the curve in I forget what year it was, but at a fairly sort of early part of the curve, he said that the U.S. is going to reach the peak just a few years later. And it seemed like a ridiculous prediction. It's like those people that predict that the universe is going to, or the economy is going to collapse when such and such happens. He's kind of like one of these sort of loony theories. But it turned out that he was exactly right, and the real peak for the continental U.S. came right when he predicted it would. So you're going to be playing with a model, one of the three for next week that's new to you, that lets you kind of do this kind of curve fitting and see what the implication is for when peak oil will happen for the whole world. So you'll put in, you'll have data, and you'll get to fit a curve to the data, and you have some estimate of the total amount of petroleum in the world, and then from that it'll give you when the peak should come, and then you can try to figure out how much kind of wiggle room there is in that. Now, one fairly fundamental objection to Hubbert's peak is that it's not a theoretical sort of a thing. It's not like black body radiation from quantum mechanics. You can calculate exactly that curve, and it's you can trace it back to the fundamental physics of a black body in quantum mechanics and all of that. So that's real solid. That's like the gold standard in science is to go all the way back to the fundamental mechanisms. But here, the rate of oil extraction depends on all kinds of things, like extraction in Iraq sort of plummeted when the war started. Extraction in Venezuela depends on how Chavez is feeling. There's all kinds of sort of social and political things that go into it. And so this curve is not a theoretically, solid thing. It's what they call empirical, or sort of observed, or just kind of the way things, tend to be. So it's perfectly possible that the rate of extraction for the whole world oil may not follow this curve exactly. Hubbert's peak can be wrong. It's just kind of a way to guess, or a way to bet, if you had to make a bet on it. What it says is that, well, there's two sort of salient conclusions. One is that the peak comes when the oil is half gone. So this R2P ratio, that's essentially trying to estimate when the last drop of oil comes out of the ground, and says 40 years from now, barring finding any more oil or changing the rate of extraction or whatever, just keeping everything sort of as it is. This is kind of a different thing. The peak extraction and shortage comes when the growth in demand is continuing to grow sort of exponentially, and if the bell curve sort of flattens out and lays over like that, then the shortage is actually kind of around the time of the peak, the time when the rates of extraction can't get any higher, when they're sort of pumping it out as much as you can. So if you talk to oil company executives or somebody like that, analysts, Daniel Yergin, the guy who wrote the prize, is not a believer in peak oil theory. He will say, well, the rate of extraction of oil today is entirely because, they didn't invest in infrastructure, refineries, and we could easily, bring out more oil if we wanted to. So he personally doesn't buy the empirical Hubbert's peak model. But still, it's a very interesting thing to watch. What you find when you start to get to the peak and start to get shortages is that prices tend to they go up, for one thing, because of supply and demand, but they also get spikier. So, the spikes in oil prices last year may have been kind of a harbinger of peak oil. And if I could get my computer plugged in, I would show you that there's a nifty figure of peak oil for whale oil that I found on the internet and put in the textbook. So the rate of extracting oil from whales, which they used for lighting, before they started using like real oil, has this amazing Hubbert's peak sort of a shape to it also. So that's kind of the story of oil as far as it goes. And then the third kind of fossil fuel is natural gas, which is mostly methane. So the amount of natural gas in traditional sort of deposits we already talked about, it's sort of a few hundred billion metric tons or gigatons, so it's comparable to oil and less than coal by something like a factor of 50. So coal is the heavy hitter. Oil and natural gas by themselves wouldn't be enough carbon to just totally cook the planet. Really, the big question, I can't stress enough, is coal. Natural gas is kind of funny in the energy infrastructure in that it's difficult to transport. Because it's a gas. So you can either have compressed natural gas, in a cylinder, like a scuba tank, And it's very high pressure in there, 3,000 psi or something like that, pounds per square inch. If you were to break it, it would explode. It takes a very heavy walls to hold in that much pressure. Or there's also liquid natural gas, where they cool it down enough to make it into a liquid, and then you still have to sort of hold it under pressure, and you don't want heat to get in there because at room temperature it doesn't want to be a liquid, it wants to be a gas. And so these are sort of the two ways of transporting natural gas around, and they're both expensive. So the price of natural gas depends very strongly on where you are on Earth. And there are some places where natural gas is worth nothing because the markets are so far away where you could sell it that to transport it from where it comes out of the Earth, like Siberia is a good example of this. And so a lot of times if there's natural gas that is associated with oil, and it's not economical to capture and transport and then sell the natural gas, they just burn it in place. It's called flaring. So price depends on location, price, I guess value, and some places it's not really worth anything, and so it's flared, which is burned to CO2 and then just released to the atmosphere as CO2. So there's one last sort of point of comparison among the three different kinds of fossil fuel that I want to make. And then we're going to talk about methane in the atmosphere as a greenhouse gas. And that has to do with this sort of spectrum of oxidation states of carbon. So CO2 is oxidized, the most oxidized form of carbon, and in an oxygenated atmosphere like ours, it's the stable form of carbon. CH4, methane, is the most reduced form of carbon. So if you bond that carbon with all hydrogens, that's giving it as many electrons as it can possibly take. It's got 4 in its outer shell. Hydrogens give it, 1 more each, 4 of them total. So then it's got 8 in its outer shell. It doesn't want any more than that. So you can't possibly make it any more reduced than that. So this is sort of the spectrum. And then in the middle of the spectrum, we had biomass, what gets produced by photosynthesis, which is kind of at an intermediate oxidation state. So let's see, -2 for each oxygen. The carbon here has to be +4. Here the carbon is -4. Here the carbon is equal to 0, the oxidation state of the carbon. Because, it's losing 2 electrons to the oxygen, but it's getting 1 each from the two hydrogens. Now, coal is mostly just elemental carbon. So we just sort of write that as C, a whole bunch of C together, in some sort of a blob, kind of a, amorphous, random, messy sort of structure. Diamond is also pure carbon, or graphite, but those are crystals and ordered and a little different, but they're all sort of carbon. So coal kind of has an oxidation state of about 0. And then oil is long chains of carbon. And the ones in the middle, which is most of them, are attached to 2 carbons and also each one to 2 hydrogens. So oil is probably, so the average carbon in oil is something like let's see, where will I put it? Right here. Oil, the average carbon in a chain of oil is sort of CH2. So the oxidation state of this carbon right here, for example, is -2 because it's getting one electron from each of the two hydrogens, but it's not really doing anything with the carbons that it's bonded to. So they sort of share equally, the two carbons, the electrons. So there's no contribution to the oxidation state there. So we have this sort of spectrum of oxidation states of the fossil fuels, where coal is here, and then oil is here, and then natural gas is there. And the more reduced it is, the more energy you get by oxidizing it back to CO2. So less energy burning the coal and more energy burning the natural gas. So one way to think of it is the number of electrons that go to the carbon. Another way to think of it, which is equivalent, is that if you burn just coal, you get energy because you're making CO2. Whereas if you burn natural gas, you make CO2 plus the hydrogens there get made into water, and you get energy from that too. So I don't know if you ever made hydrogen in, like, science class by electrolysis, and then you stick a stick in there that's got a hot ember on it, and it makes the hydrogen explode. It was a real formative experience for me in like middle school, because you make explosions in science class. So making water out of hydrogen gives you energy. So making water as well as CO2 is more energy. It turns out that you get about twice as much energy per carbon molecule, carbon atom, by burning gas than by burning coal. So there's they talk about methane gas, natural gas, as being a cleaner fossil fuel than coal. And it is in several ways. One, coal, when you burn it, releases all these sulfate aerosols that affect the climate and then become acid rain. It's all this mercury. Coal mining is intrinsically an ugly process, especially when they do these like mountaintop removal things. Natural gas, you get less carbon per the amount of energy that you produce, and it's also, it doesn't have as much sort of other baggage like the sulfur and the mercury and stuff with it. Yes? Mercury likes to form a sulfide. There's a whole suite of elements that, if there's no oxygen and the sulfur is turning into sulfide, hydrogen sulfide is some of the stinkiest stuff in the world. You can smell better hydrogen sulfide than any detector can tell, because it's very poisonous, and it sort of comes up in our environment, that we evolved in. So in a place where you're preserving coal, there's no oxygen there. That's why the organic carbon from the photosynthesis gets preserved. And that also tends to make sulfide, and that tends to trap elements like mercury and cadmium and lead and others like that. So it tends to travel. It tends to concentrate in those sort of dark, smelly, anaerobic places where we get the fuels from. Okay, so natural gas is cleaner than coal for energy, but natural gas is still a source of carbon, and in fact, the methane itself is a greenhouse gas. So just to kind of review what we learned when you're talking about greenhouse gases, it is something like 30 times more powerful than CO2 sort of comparing one molecule of methane to one molecule of CO2. And that's because there's much more CO2 in the air. So CO2 is more band saturated than methane is. So the methane, the way it behaves when it's released to the atmosphere is it is a transient gas. It gets released to the air, and then it has a lifetime of about a decade in the atmosphere before it reacts to make CO2. After about a decade, the CH4 reacts to make CO2. And when it does that, it loses most of its, the carbon atom loses most of its greenhouse power because it's now a CO2 molecule instead of a methane molecule. So so the source of methane to the atmosphere is it's sort of like a driver. And the sink where the methane goes depends on the methane concentration. So this should look sort of familiar to you, actually. This is yet another example of where we can apply our wonderful sink analogy. So there's the faucet. There's the sink. You have sources of methane that are putting methane into the atmosphere. And then the sink depends on how much methane is in the atmosphere. Because if you have a high concentration of methane, that means you're reacting more molecules per second or whatever than if there's no methane in the atmosphere. So the water level in the sink represents here the methane concentration in the air, and then the going down the drain, that's reaction in the atmosphere making CO2. So let's say that we had the methane concentration in the air as a function of time. And let's say that we started out with sort of a steady concentration of methane in the atmosphere. So it's not changing as a function of time. And now we're going to, at this time, we're going to add some new sources of methane. What happens is, so say the source goes up like this. And then the concentration will sort of rise until it is enough to make the sink for methane. Let's see. So we'll call this a methane rate. And we'll put the methane concentration in another plot kind of up here. So we suddenly increase the source, and then at that point, after you've increased the source, there's more going into the air than going out, and so your concentration is going to rise. And as the concentration rises, the reaction rate of converting it, of burning it essentially to CO2 rises until it sort of balances the source rate. And the time scale for this is about the 10-year lifetime of methane in the atmosphere. So just like in the sink analogy, two ways of changing the water level in the sink. One is with the faucet, the sources, that's what we just did here. The other is with the sink, if you change the chemistry of the atmosphere in some way. And it turns out that most of the discussion about the methane concentration in the air and how it has changed involved new sources. Sources of methane. There are natural ones. There are human-caused ones. And there's also the possibility of sort of climate feedback sources. So the biggest natural source of methane is swamps. Methane is called swamp gas. So if you step in some really muddy, yucky, gross swamp or shallow water, lake, mud sediment or something, a lot of times you'll see all these bubbles coming out. And that's methane. Methane catching fire in swamps is, that's the explanation you always hear for UFO sightings. It's just swamp gas. And so it burns because it's methane. There are other sort of natural sources that are much smaller. Termites and ruminant animals, like natural ones, deer, moose, or something like that. As part of their digestive strategy, they harbor a consortium of bacteria that can digest cellulose, which is something that we can't. I mean, we can't eat wood and digest it, even though there's energy in that wood. That you burn wood in a campfire and get energy from it, but you can't eat it because we don't have the enzymes to digest that. So, or grass, for example. So the way that cows eat grass is they have bacteria that they host that have the enzymes, and they sort of do some of the digestion for them. As part of that process, it releases methane. So under human-caused, one of the sources are livestock. So it's not strictly speaking cow farts. I told people for a long time that cow farts were this source, and this was a question that nobody ever missed on the exam. It was just an astonishing thing. So once you've heard that, it's in your mind forever. There's nothing you can do about it. But it's actually not true, because where the methane comes out in a cow is an exhale, from the front end rather than the back end, as it turns out. So the one fact that I was very successful at conveying was wrong. I just have to live with that truth. There's a human sort of analog to swamps, which is rice farming. It turns out that rice doesn't, require living in a swamp, but it tolerates standing water better than a lot of the weeds that can confound rice agriculture. So a lot of times rice is grown in sort of standing water, and this makes a big source of methane to the atmosphere. There's also methane released from fossil fuel industry. Like we talked about flaring natural gas. Well, maybe they don't always, get around to burning it. Maybe some is just released. If you walk down 57th Street, there's this apartment building called the Muse, and they've got these very fancy gas lights out by the sidewalk. little mantles, and they glow. And sometimes the little mantle, which is a little bag of string, breaks. And in that case, the fire goes out, and you can smell as you walk down the street this natural gas coming out. And it just really irritates me that they would just cavalierly put methane in the atmosphere. But we would call that, I guess, fossil fuel source. And then there's a potential for climate to change things in ways that may add methane to the atmosphere. And the most prominent source is permafrost melts that has with peat. So there are peat deposits that are accumulating in the high latitudes today in Canada and Siberia and places like that, and they're preserved by being frozen. So you can put some leftover food or something in your freezer, and it will preserve it. It'll keep bacteria from eating it. So I've even heard about somebody finding an intact woolly mammoth that's been frozen for 20,000 years up in the high, somewhere, and it was thawing out, and they actually ate a steak of this, and it was kind of gross, but it was still perfectly edible. It was still preserved. Freezing sort of preserves organic carbon. So these permafrost soils have been preserving organic carbon for thousands of years, and now if they start melting, it may decompose and start releasing methane to the atmosphere. And then there's also, on very long time frames, these hydrates that we mentioned last time. So these are these ice deposits in ocean sediments. And to melt these and release carbon or methane, it would take sort of thousands of years. So those are the sources of methane. The sink is this chemical reaction, and it's very interesting chemistry because it all has to do with these radical compounds. So CH4 gets attacked by this radical, which is called, it's OH. So oxygen really wants to be H2O. It's not happy being OH. That's a very unstable, it's a radical compound. It's only found where there's sunlight that sort of blows molecules apart, and it has a lifetime of microseconds or something like that before it finds some way to steal another hydrogen and go back to being water. And one of the things it can steal hydrogen from is methane. So so now the oxygen there and that hydrogen are happy because they've made water, a nice sort of little family there, a nice stable molecule. And now this one, the CH3 is a radical. So someone asked the other day if you can have 3 bonds to carbon instead of 4. You can, but it's a very unstable compound. It's a radical. And so once this CH3 is formed, it then attacks somebody else, and it very, very, very quickly, through a series of reactions, gets oxidized to CO2. But this is sort of the first step, and then after it happens, the rest of it is all just very quickly. Now, the thing about this chemical reaction is that this OH radical has the potential to be affected by all kinds of other changes that have happened in the atmosphere. So OH is produced from ozone, which, there's more ozone in the sort of lower atmosphere, especially in sort of smoggy urban environments. There are these ozone alert days in the summer. They tell us not to go outside running because it's worse for you than sitting there and watching television, I guess, because there's this ozone in the atmosphere, and it messes up your lungs. So ozone is changing. It's also produced by these nitrogen compounds called NOx. So this is a family of NO and NO2, which come from car exhausts. And it's one of the components of urban smog. So you get this nitrogen compounds coming out of tailpipes, and then you shine sun on it, and it makes this sort of brew of nasty chemicals in the atmosphere and make ozone. And then another thing that affects OH is carbon monoxide. Which comes from things like fires. So there are more fires in the world than there would be naturally because people cut down trees and burn them in order to do agriculture. So all of these things seem like they ought to be changing the concentration of OH, which should be changing the lifespan, the lifetime of methane in the atmosphere. And so that would be like messing around with the drain of the sink analogy. But it doesn't seem like there have been any big changes in the lifetime of methane in the air. And it seems like there's all these sort of factor of 2 changes in these drivers for methane that seem to sort of cancel each other out by sort of coincidence. So what the methane has actually done in the air is it has sort of doubled from the pre-industrial value of from the year 1750, but it sort of stopped rising actually in about the year 1993. So it was going up, and it looked like it was going to keep going up, and then it sort of defied all expectations and kind of leveled off. And it's not clear why it did that. One theory is that this was around the time of cleaning up the former Eastern Bloc, leaky oil or gas pipelines and inefficient industry and things like that, decreasing the source. Another theory is that the planet has been sort of drier since then, so maybe there's less of a source from swamps. But at any rate, it's kind of a mystery, and it's not clear. It looks like it's actually started going back up again just in the since about 2007. But it's not clear what, it's sort of a loose cannon in the whole climate system. It's not clear why it stopped going up or why it started again. So we'll leave it at that.